welcome. We're going to do 1.6, so here we go. Okay, 1.6 is on finding limits using the limit laws. And so they have all these laws, limit laws in your textbook. The key here, and this got over here, this key to the whole situation got on, and I always say I'm going to fix that, but the key here is that this and this have to exist. They can't be going to infinity, can't be going to negative infinity, can't be, does not exist because the left side doesn't match the right side. So the key is that it has this has to exist and this has to exist, and then these things are true. My brother told me about the autofocus, and he says that's my problem, and it's my hand and the autofocus, he said. See, when I raise my hand up high. And so he has a suggestion of how to fix that. Of course, I didn't get that for this video, but we'll hopefully have it for the next video. So that if you're trying to find the limit of a sum between two functions, you can find the limit of the functions individually and then find the sum, and it would be the same. Same with a difference or a subtraction. Same with multiplying by a constant. You can bring the constant out in front and find the limit of the function at a, and then multiply it by your constant. Multiply two functions together. Can find the limit of the multiplication by finding the limit of the pieces and then multiplying them together. The division, as long as g is not 0, the limit as x goes to a of, as x approaches a of g of x is not 0, because you wouldn't want to divide by 0. Same with if you're trying to find a function raised to a power, that you can find the limit of a function raised to a power. You can first find the limit of the function, then raise the whole thing to a power. If you're trying to find the limit of a constant, that's a constant. If you're trying to find the limit as x goes to a of x, that's just equal to a. So all these limit laws. This is for this one has to do, and also this one has to do with that it's okay to substitute, right? So these three right here look like what you're doing is substituting in, right? Substituting in a for x. And they say that's okay to do if you have a linear function, if you have a polynomial function, and if you have a root function. And so on it goes. And we're going to practice these a bit, these limit laws. So we'll see how we do on them. So here they were wanting me, this is an example. Just the book had just, just a few examples, and so I made an example up out of myself, but they were wanting you to use the limit laws and state what law that you were using. And so I'm going to state the laws by number as they're given here, as I use them. Okay, and so I'm looking here, and it's telling me to find the limit as x goes to 1 of the cube root of this. So the first thing that I would like to use is law number 10. So I'm going to put a 10 here. This is the one I'm using. And number 10 says that if I have a root, right, oh no, it wasn't number 10 that I wanted to use. It was this one, number 6, that I wanted to use. And I'm going to take that, I'm going to write my root as an exponent, and then I'm going to apply, instead of I'm going to apply it to the outside of the limit. I can't say that very well. So this is not really 6. So I really want to write this like this first. The limit as x goes to 1 of f at x times g at x plus 3 raised to the 1/3. Then I want to apply number 6 to that and write this as raised to the 1/3, the limit as x goes to 1 of f times g at x plus 3. Okay. So that's my first thing, is to take this and apply it outside of the limit, apply it after the limit, the raised to the 1/3. And now I'm going to use my property number 4, no, my property number 1 for breaking apart this addition. So number 1. So this is the same as, that's my equals, and then this is going to be the limit as x goes to 1 of f times g at x here. So that's going to be the 1 limit I'm going to be finding, plus the limit as x goes to 1 of 3, all this raised to the 1/3. So I applied property number 1, saying that if you have an addition here, that you can break it apart and apply because I know that f times g exists because it was given up here to exist, it has to exist, and I know the limit as x goes to 1 of 3 exists, so it's okay for me to break that apart. And here I knew that exists too. So now I am going to use number 6 and number 4. So number 4 equals, now I'm circling a different thing, but number 4, property number 4, and this is going to look like the limit as x goes to 1 of f at x times the limit as x goes to 1 g at x plus the limit as x goes to 1 of 3, all raised to the 1/3. And now I know what this is equal to. And so that is equal to 8. And I know what this is equal to because it was given. It's equal to 3. This was too much information on this particular problem. I didn't have any h in here. And I know what this is equal to by property 7, right? So by property 7, number 7, tells me that this is equal to 3 because this is the limit as x goes to 1 of a constant, right? But my constant is 3, and they said that when I had a constant, this would equal the constant, but my constant is 3. And so this is equal to 3. So this is going to be 8 plus 3, no, times 3 plus 3, all raised to the 1/3. So now I've done the limit. It's 24 plus 3 is 27. 27 raised to the 1/3 is 3. So this is 3. And so that's kind of what they were hoping, is that I would just tell them what limit law that I used as I went along there. There's more for you to practice if you want to. And then this is the direct substitution property. It says if f is a polynomial or a rational function and a is in the domain of f, then the limit as x goes to a of f of a is equal to f at a, which means you can just use direct substitution as long as you just have a polynomial or a rational function. And so then I wrote in my own little words here the direct substitution property in words. You can use direct substitution to find the limit of a linear function, because that's a polynomial, or a polynomial function, or a rational function, provided, so on the rational function, provided the denominator isn't 0, because they said in the domain. And so if the denominator on a rational function is 0, then you wouldn't be able to use direct substitution. So we're going to look at that here on, this is problem 4, and I also put some graphs on just so that we can look at what they're asking, what they were wanting. So this says the limit as x goes to -1, and this is just a polynomial, and so this is actually a polynomial, and that's a polynomial, and so I can just use direct, and you multiply two polynomials together, you're going to get another polynomial. So it's okay to use direct substitution. So this would be equal to -1 raised to the 4th minus 3 times -1, all times -1 raised to the 2nd plus 5 times -1 plus 3. And so I'm going to put -1 in here, in all these places, right? And I'm going to just grab a calculator and do the math and see how that goes. And I hope that you guys are doing it as well. If you're not doing it with your calculator yourself, then you're missing out on an opportunity. And so make sure that you do practice putting these things in your calculator. I can't tell you how many times that people will come during a test and say, you know, I got the calculator that you asked to get. Any scientific calculator is good, but, you know, I got the one that you like, and I haven't practiced with it at all, and I don't know how to use it. So I got -4. And so how you avoid that is by practicing using it. It's pretty friendly. You pretty much put things in like you see it. The only tricky part is right here where you put in the raised to the 4th. That part can be a little bit tricky, because see how I'm upstairs? There I'm on the exponent, and if I typed in the minus next, it would just be right upstairs with that, and I didn't want that. So I'm going to delete that. So I'm going to hit the delete key, and what you have to do is you have to hit the to the side, and that takes you down. Anyway, so that's other than that, I don't think it's too terribly tricky. So what we just found is when we were here at -1, that our output was -4. So this is the graph of y equals that. So you can tell that I can't really tell if that's correct from this graph. So this is the big picture graph, and so I kind of zoomed in over here. I use Desmos to graph things, and I wanted to, here I am at x is -1. There is not a hole in the graph, and so here is my output, and that's what the limit is asking. It's saying as you near 1 from the left and from the right, whoops, from the right and the left, I went backwards on that, the output is nearing -4. That's what the limit is saying. And the direct substitution property said, if this is a polynomial, then you can just substitute to find what it's nearing on the left and what it's nearing on the right. And so this is, I just put this example in here just while we were thinking about it on graphs. The limit as x goes to 6 of 4, so the limit of 4. And remember the property, this property, it takes some getting used to for a lot of people, that this is equal to c. And so this is equal to 4. And you might be sitting there thinking, well, why? And I want to draw y equals 4, so I already have what I'm going to draw here to show you why. It's like when you make the drawing, it'll make perfect sense. So y equals 4 is a horizontal line, 1, 2, 3, 4, here at 4. So it's a horizontal line. So there's the graph of y equals 4. And here I am at 6. And as I get close to 6 from the left and get close to 6 from the right, you notice the output, that's what the limit's asking us, what's the output getting close to? So as the input gets close to 6 from the left and from the right, what's the output getting close to? Well, it's getting close to 4. And so that's why that property. Okay, so this is problem 8. And so I can apply limit properties to break this all apart, but I usually don't. I usually say to myself, okay, this is a rational function raised to the second. As long as the denominator is not 0, it would be okay for me to use direct substitution. So what is the denominator here? So let me see what it is. So this would be raised to the third minus 3 here plus 5. So let's put a 2 in here. And I can see that, hey, that's 8, take away 6 plus 5. That's not 0. So it would be okay for me to use direct substitution to find this limit. So I'm going to go ahead and put in t is 2 up here as well. And then I just plan on putting that in my calculator. And so all of these were possible using the direct substitution property, right? Okay, so even this is the direct substitution property. That's just a line, right? And so plug in x is 6 and tell me what you get. Well, there's no place to plug in, right? So we just get 4. So over here, what do I want? I want parentheses, and then I want a fraction. Oh, how did I do that? I want parentheses, then I want a fraction. I don't know how I got that in there. The parentheses are not necessary here because it's not a -2. -2 in the numerator. And then downstairs, 2 to the third. And then -3 times 2 plus 5 and raised to the second. And I get 4/49. Did I raise it to the second? I did. 4/49. I should have known that's a perfect square. Okay, we found the limits here using the direct substitution. I think that's how you spell substitution. So anyway, now we're going to look at some where you can't use direct substitution, if I'm remembering correctly. And so you have to be careful and you have to think, and don't blindly use direct substitution on everything. And when things that could give you problems, that's what I'm trying to say, are function with even roots. The greatest integer function or the least integer function could give you problems, and also functions that are piecewise defined. And I'll be careful, we'll be careful when functions have even root. And so, for example, if I ask you to find the limit as x goes to 2 from the right-hand side of the square root of x minus 2, then here, because if you stay bigger than 2, this square root is always positive. So I'm going to think about the table method just so that you can kind of see the idea. So I'm thinking about the table method, right? And so if I'm bigger than 2, so maybe I would be at 3, right, for example. And then my limit, my output, my y, I'll put my y is what I'll put. My limit, this is what my limit's going to be, is my output, right? That would be 3 take away 2 is 1. The square root of 1 is 1. And if I did 2.5, that's getting closer, but still positive. That'd be the square root of half. And I don't know what the square root of half is, but you could do it on your calculator if you liked. And if I did 2.1, so I'm getting closer to 2, but staying bigger than 2, that'd be the square root of 0.1. And there's nothing wrong with that. I could certainly find that on my calculator, right? And I could even put some zeros in there, right? And then that would be the square root of however many zeros I have in there. 3 of them I think I have. I might even be able to find the square root of those things myself. And so that's the idea, is that, hey, that would be fine. And this over here, if you're figuring out what that is getting very near to what? So if you figured out what these were using the calculator or your head, whatever you use, what is, as this gets closer to 2, right? As I approach 2, but stay bigger, what is this approaching? What is that going to? That's my question mark. What is that approaching? And I agree with you, it's approaching 0. And the reason that it was okay for me to use direct substitution, 2 in here, right? And 2 minus 2 is 0, and the square root of 0 is 0. And the reason it was okay for me to use direct substitution is that the underneath part of the radicand was always positive. And so it was okay. So for every value that I would have put marching in to 2, it would have been positive. Whereas this is not going to be the same answer. This is not going to be equal to 0. And the reason is that if you think about the table method and you start putting values in, like 1.99, for example, 1.99 minus 2 is the square root of negative, is it 0.01? I hope it is. My thinker is thinking about breakfast at this point. Yes, it is negative 0.01. And you can't take the square root of negative 0.01. That's undefined, right? And so anyway, so that's the issue there. And so the idea here is that would be does not exist. It's not equal to 0. So if you use the substitution method, then you might think, well, it's 0, but the substitution method wasn't appropriate to use here. If you think about the graph of this thing, I'm going to quick sketch it. It's half a parabola. I know that from my when I used to teach Math 1, right? This is one of the main graphs of pre-calculus or math analysis, is like y equals some square root, like that. So it looks something like this. And so as long as you're on the right side, you're going to be able to find the limit. But if you come over here on the left side, the function's not even defined. And remember, when you ask a limit, you're not asking what is happening exactly to, you're asking what's happening a little before to and a little after to. And so it's okay to use direct substitution if you have a polynomial or if you have a rational function that's in its domain. And it turns out that as long as you're in the domain here, right, as long as you keep things so that when you're marching in, you're good, you're square root of a positive, you're okay there. We'll look at the greatest integer function, I promise. And so I told you some problems that you can go and try and be ready to discuss those. If you want, you can. My office hours or in class. So be careful of a function that are piecewise defined. And so you have to be careful of those. And the reason is the same here, is the little before and the little after. So if I ask you to find the limit as x goes to 1 from a little bit smaller than 1, so I'm looking here and this says use x as your output if x is smaller than 1, right? So this would be perfect. So this would be the limit as x goes to 1 from a little bit smaller than 1, and I'm to use x for my function. Well, that's just a polynomial, not a very exciting polynomial. So I can use substitution. So I substitute in 1 and I get 1 as my answer. This one, on the other hand, this is saying, is asking me to compare, right, the limit as x goes to 1 from a little bit smaller than 1 versus the limit, because it says from both sides, as x goes to 1 from a little bit bigger than 1. So for the same reason that we did over here, this is saying the limit as x goes to 1 of x, which using direct substitution is 1. But from a little bit bigger than 1, this is exactly equal to 1. And this is a little bit bigger than 1, so this is the one I would use. So this is the limit of 2 minus x squared as x goes to 1 from a little bit bigger than. And so since this is a polynomial, I can use substitution. So this is 2 minus 1 squared. People always ask, what do I plug in when it's a little bit smaller than 1, when it's okay to use direct substitution, and when it's a little bit bigger than 1, and it's okay to use direct substitution? And if it's okay to use direct substitution, it's okay to plug in just 1. And so here we get 2 minus 1, which is 1. Now, because the left limit, this was the left limit, and the right limit both exist, and they're both equal to 1, then that means that this is equal to 1, right? And so these two together tell us that the limit as x goes to 1 of g of x is equal to 1. You might be saying, what if these weren't the same? Then what would I do? And good news, that's the next problem. So on the next page, so we back to problem 52 there, and I ask you, what is g at 1? And this is not saying a little bit before 1, a little bit after 1, like a limit would. This is saying exactly at 1. And so this is what I would use if I was exactly at 1. So this is equal to 3. And I'm not sure why I gave you so much room here. And so maybe it's so that you could doodle something or whatever have you. Maybe I was going to put arms on this character that I made. I think I need a big smile for sure on my friend there. I have some shoes too that I've drawn. Maybe some hands. I don't know why I gave so much room there. Okay, so now if I'm going to 2 from a little bit smaller than 2, so a little bit smaller than 2, then I would use 2 minus x squared. So this is, and so this is not saying from both sides, this is saying from one side only. So this would be the limit as x goes to 2 of 2 minus x squared. And this is a polynomial, so it's okay to substitute in, and I'll substitute in 2. So I'm going to get, for this answer, 2 minus squared, right? And I'm going to plug in 2. So this is 2 minus 4, which is negative 2. So that would be my answer there. This is saying from a little bit bigger than 2. So I notice that a little bit bigger than 2 is x minus 3 is the piece I would use, right? And so a little bit bigger than 2 on my piecewise define. This is polynomial, so it's okay to substitute. So 2 minus 3 is negative 1. So I could have wrote it here too. 2 minus 3 is negative 1. However you want to write it, it's good. I don't know. I just felt like I needed to be consistent with how I wrote it there, but they're both good, I think. So there's my answer there. Now, when it asks you to find the limit as x goes to 2, it's asking you to compare the left limit, right, which was this, which was negative 2, the left limit, versus the right limit. And you have to make sure that when it's piecewise defined that you do look at the left limit versus the right limit. And so the left limit was found here, and the right limit was found here, right? And that was negative 1. And only would this limit exist if these were exactly equal to one another, which they're not. So we know that the limit as x goes to 2, g of x, does not exist. So that would be our answer. And the last one they ask us is about 5. And 5 is because it's not an endpoint. Both before 5 and after 5 are using the same piece of the function. You would use this piece of the function if you were nearing 5. So here, when I was nearing 1, I had to be careful, right? When I was nearing 1, I had to be careful that there was a left piece and a right piece, because 1 was kind of on the end point, right, of 2 pieces. It was the divider between 2 pieces. I have to also be careful with 2. But any other number I won't have to be as careful with. So like if they ask me to find the limit as x approaches half, then I would be fully in this category, both from a little bit bigger and a little bit smaller, and I would just use this. And 5 is the same way. I'm fully in that category. So I don't have to compare the left and the right because it's the same. I'll just use this piece. So this is the limit as x approaches 5 of x minus 3, which using substitution is 5 minus 3, which is 2. And I didn't have to show both sides because it wasn't using 2 different functions. So it would kind of look silly if I showed both sides, because it would look like this, right? So this would be silly. But it would look like this. From a little bit smaller than, you would use this function. And from a little bit bigger than, you would use the same function. And so that's why I say that it's silly. So of course, if you substitute in, you're going to get the same value. You're using the same function. So it's not necessary to show both sides, even though it was piecewise defined, because 5 wasn't an endpoint. Okay. Then, finding limits of rational expressions. What if when you substitute, the denominator is 0? And there are 2 cases. It's when you have a hole in the graph versus if you have an asymptote. And we're going to be looking at these two cases in chapter. I got bit by a mosquito and now I can't stop itching it, and I'm thinking to myself I might have to stop the video so that I can go and put something on it so that it can drive me crazy. But there's different stories based on whether you have a hole or an asymptote, and we're going to be learning about which one is which. You might have learned which one is which in pre-calculus. I hope you did. But for sure you're going to learn here. And so this is the first case we're going to look at, the limit as x goes to a of f of x. When you substitute in, if you get 0 divided by 0, this is called indeterminate form, and it needs more investigation. My suspicion when I get 0 over 0 is there might be a hole in the graph at a. It also might be a vertical asymptote at x equals a. And how you find out which one it is by simplifying. And so if you got how you simplify, if you got a rational expression, then you might be able to factor the numerator and the denominator and cancel out a common factor. If you got square roots, you might be able to rationalize the numerator and the denominator. You may need to multiply by the conjugate. Then you will have this, and you'll be able to cancel out hopefully you'll have this, and you'll maybe be able to factor and cancel out a common factor in the numerator and the denominator. If you got complex fractions, you can simplify those complex fractions any way you know. I like to clear fractions, method 1 versus method 2. If you got stuff that can be added or subtracted or multiplied or divided, you should do that. And when you do all of these things, you're hoping then that you might get something where you can factor it and cancel from the numerator and the denominator. If you got absolute value, you might need to use the definition of absolute value. And then once you've simplified, then it may be that you can use direct substitution. And so you might be able to find the limit using direct substitution. So that's what we're going to give a try to. So we're going to try these using the limit laws again. So when I try the direct substitution here, that's when I notice that direct substitution isn't all that it's going to take to find the limit, because the first thing I'm going to notice is that the denominator, when I plug in here, is equal to 9 plus 3 is 12. Take away 12 is 0. The denominator is 0. So that means that I can't use direct substitution to find this limit without doing something else first. So I'm gonna work on this a little bit. So what I want to know is this 0 in the numerator or not? And it either is or it isn't. And if it is, and then it's the case we've been talking about that we're trying to investigate right now. And if it's not, then we're a little bit ahead. I'm going to show you how to do that as well. So don't worry. So it is. It's 0 over 0. And so right now, my limit is indeterminate. And so I don't know what the value of the limit is, but I think that it probably exists, and I just need to find it. And so since this is just a polynomial divided by a polynomial, I can perhaps factor the numerator and the denominator. So that's what I want to do next, is I want to factor the numerator and the denominator. So the numerator is factoring out an x. I get x plus 3. It has a greatest common factor. And the denominator does not have a greatest common factor. So when I factor that, let's see, to make 12, 4 and 3, right? Make 12. And yes, when I subtract them, I get 1 here. So I want a minus here and a plus there. So I think I want this to be x minus 4, x plus 3. So the x plus 3's will cancel out. If your factoring is like, you're saying, oh my gosh, I struggled to factor, I don't remember how to factor, come get help from me. Go get help from a tutor in the Math Learning Center. Go get help from a tutor in Mesa. go get help from a tutor in the drop-in tutoring that they have in through the student services. All of those are on your syllabus, places that you can go to get help. And so coincidentally, nicely, I'm so happy, x plus 3, when I divide it, is gone. So now I'm asking you to find the limit as x goes to negative 3 of x over x minus 4. And so now this is one, I've converted it by reducing, by simplifying, into one that I can use substitution, because it's okay to use direct substitution if your denominator is not 0. And so now I've converted it from 0 over 0 to something that doesn't have 0 in the denominator. And so now I can just plug in. So this is this over this, right? And you plug in negative 3. And I know the parentheses weren't really necessary here, so that's negative 3 over negative 7, which is 3/7. So there's my limit. And I just wanted you to check it out on a graph. So if you graph y equals x over x minus 4, this was the last one that we found, this is what it looks like. And if you graph this, the only difference between this graph and this graph is that there's a little hole in the graph at x equals negative 3. So right here, negative 1, negative 2, negative 3, there should have been a little hole in the graph right there. And one of my students from last semester told me how I can make a little hole in the graph on Desmos, and I need to go and do that. I almost think, though, and you guys might send me how to do it too, because I do have the how to do it from him, but I do think that I want you to know that there's a hole there, and we're putting it in. Now, this graph had an asymptote, and that asymptote is at x equals 4. And so here it is, the asymptote. This graph also had an asymptote at the same place, x equals 4. So this graph, when we graphed this, had two things. It had an asymptote and a hole. It had a hole at the place where we had a common factor, and we were able to reduce out the common factor. And so you have a hole where your denominator is 0, but also has a common factor with your numerator. So my denominator was 0 at x equals negative 3, but x plus 3 was a common factor with the numerator. And we have an asymptote where your denominator is 0, but there is not a common factor with our numerator. So if I asked you to find the limit as we near negative 3 from the left and from the right, it doesn't matter if it's a hole in the graph or if it's solid. Remember, that's what they were telling us in the intuitive definition of a limit. If you're nearing negative 3, it does not matter when you go to find the limit if there's a hole in the graph or if there's not a hole in the graph. So here, I couldn't use direct substitution, because if I use direct substitution, then I would get undefined because of the hole in the graph there, right? But these two things have the same limit, so I can convert this into this and then use direct substitution on this. So that's kind of the idea. And I don't know how to make Desmos draw correctly with the hole. If you do see me, you can email that to me, but I have to tell you that this is no longer a true statement. I actually do know how to do it. I just haven't done it yet. And so that's a different story, right? Okay. Note, the only difference in the graph of y equals this and the graph of this, just to make sure that everyone is there's a hole in the graph that occurs at, and then this is either x equals negative 3, or you could write this as an ordered pair at negative 3, and I think this is what they were wanting, was the ordered pair here. 3/7 was the hole in the graph. That's where that hole is at negative 3/7, right? And then the equation. So I don't know if I asked you to write it as an ordered pair, but a lot of times I ask you, what is the ordered pair of the whole? And so this is the ordered pair of the whole as an ordered pair. And then the equation of the vertical asymptote is x equals 4. I often get I get just simply, people are thinking that shortcut notation, and it's not correct. Not correct. People will put 4 simply. When asked for the equation of the vertical asymptote, we'll put 4 correct, 4, and just simply 4. And that's not correct. You want to make sure, because when you say 4, you're not indicating to me a vertical line. You're not indicating to me a horizontal line. And so this is not correct to write just 4. You want to write x equals 4. Okay. Now it says, so these are more on the limit laws. I did the drawing here and investigated it, even though they did not ask you to do that on number 12, just because I wanted you to see what was going on graphically. If you want to graph this one, you can as well. And so I'm just going to do it algebraically, but if you want to look at a graph of it, if you want to look at the table method doing it, I'm all fine with that. So if I try to use substitution and I plug in that h is 0, then in the numerator and also in the denominator, I get 0. So I know it is not appropriate to use direct substitution without first doing something else. So I want to know, is the numerator also 0? And it is, because it's 3 raised to the negative 1, which is 1/3, and 3 raised to the negative 1, which is 1/3, and it's 1/3 minus 1/3, which is 0, right? So this is indeterminate. And indeterminate means you got to work harder. And so that usually means that you're going to try to simplify this so that the denominator reduces out. And when you do that is when you have 0 over 0. And so that's what I'm hoping to do. So I'm thinking, well, I should write that with the negative ones as fractions is what I should do. And so this would be the limit as h goes to 0. And I'm going to write this as a fraction. 1 over 3 minus h raised to the 1, but I wouldn't have to write the raised to the 1, minus 1 over 3 raised to the 1, all over h. And I am going to go and erase the raised to the 1 because it's not necessary, and then it starts to confuse everyone because it's kind of small there. I'm going to erase that. I hear my family talking about food, and I'm thinking, how many more pages are there? How far am I on this video? I'm thinking, finish this problem and go get some food, and then make another video with 30. So that's what I'm going to do. So I'm going to choose to clear this complex fraction by multiplying by the common denominator. In this case, the common denominator, the lowest common multiple, also called the lowest common denominator, is 3 times 3 minus h. And I'm going to multiply the numerator and the denominator by that. So I'm going to multiply this numerator by that. And because it's a binomial, so times 3 minus h. And I'm going to do this denominator, it's a monomial, times 3 minus h, right? And this is really secretly 1, right? And because this is a binomial, I have to distribute this to here and to here. Because this is a monomial, I don't have to distribute it, but I'm hoping to clean up the numerator and get rid of the fractions. So what this is going to look like when I distribute it is 3 times 3 minus h, right? I'm going to multiply that to that, times 1 over 3 minus h, minus 3 times 3 minus h, right? I'm going to distribute this to this, times 1 over 3. In the denominator, I'm going to have h times 3 times 3 minus h. And I don't really want to multiply that together because remember what I told you my goal was? My goal was to reduce out h. If I multiply this all together, then I'll have to factor it in order to reduce out h. So I don't want to do that. So in the numerator, this is over 1, right? That's a whole. And so this is 3 minus h divided by 3 minus h, which is just simply 3. And this is the 3 divides out, which is going to be, and you're going to have to be careful because you're going to have to distribute that minus to that binomial. So there's some binomial situations here. And if I had a nickel for every time that a person made a mistake on distributing something like a negative like that, I'd be rich, 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 because it's really easy to do. And so it's because of the parentheses that would be here. And so, well, that are there when just around the 3 minus h. So in the denominator, I have h times 3 minus h. And the numerator reduces down to simply h, and then h divided by h is 1. And now, all of a sudden, I don't have, if I use substitution, I have 1 now in the numerator, right? I'm going to write this again so you can see what I have. I have the limit, now that I've simplified it, of 1 over 3 times 3 minus h is what I have. And my numerator is no longer 0, but more importantly, my denominator is no longer 0. And so when I substitute in, I get 1 over 3 times 3 minus 0, which is 1 over 9. And that's my answer. Okay, breakfast, and then we'll do that one right there. Hey, if you're thinking, I think I know how to do it, then my recommendation is give it a try.